theory is good. What else do we know? The energies of these orbitals, these are known as energy orbitals. All right, so the electron absorbs energy, jumps up here, and then releases energy while jumping down. So what is the energy of the first orbital? That's the ionization energy of the hydrogen atom, which is 13.58 electron volts. So the ionization energy of the hydrogen atom is the same as the energy of the first orbital, which happens to be 13.58 electron volts. So what does it mean? Theoretical numbers match the experimental numbers. What do we do at this point? Guys, at this point, once the theoretical numbers and the experimental numbers match, the game over. Your opinion does not matter. My opinion does not matter. The older generation's opinion don't matter. Whether you shave or not, it makes no difference. At this point, what do? You just shut up. Once the experimental and theoretical numbers match, which means that those postulates the theory was based upon is also accurate, which means that there are orbitals around the nucleus within which the electrons can move without losing energy, and the electrons can also jump between these orbitals. That's it. These are the facts of life. Which means that Bohr got it. Intuitively, he had a really good understanding of what's going on. You can't justify it using classical physics, but this guy's picture of the atom is really what the atom is. It looks like. Furthermore, you can also determine the energies of different orbitals. Go back to the Balmer's series. Remember, N3 is going to give you red, N4 is going to give you a combination of blue, green, 5 and 6 is supposed to give you two colors, two shades of violet. Let's check to see if that's what we end up getting. All right, 4 spectral lengths of the hydrogen atom, so you get red, blue, green, shades of violet, 2 shades of violet. When N is 3, red, 4, blue, green, 5 and 6, 2 shades of violet. We'll check to see if that's what we got. Evidently, when the electron makes a transition between the third energy state to the second one, it's going to give you red. 4th and the second, blue, green. 5th and the second, it's going to be violet. 5th and the second, it's going to be violet. All right. In fact, if you go back and take a look at it, do you guys notice that this is 2? 2 represents the second energy state. 3 represents the third, 4th, 5th. And all of a sudden, this formula that people didn't know how to interpret started to make perfect sense because it's related to what's going on inside the hydrogen atom. All right, so this is the structure of the hydrogen atom. This is the modern hydrogen atom. All right, this is known as the Balmer series because every time an electron makes a transition to the second energy state, it's going to give you visible light. You end up getting the frequencies of different frequencies of visible light. All right. So the experimental and theoretical numbers match, and that's all you have to do in order to prove that.
The agreement between
whether it agrees with your common sense or not is irrelevant. All right, nature is under no obligation to make sense to you.
Niels Bohr's model and the experimental measurement was nothing short of amazing. Like Newton's idea of action at a distance, Bohr's model of the hydrogen atom was accepted not because it was easy to grasp or comfortable to live with. Instead, like Newton, Bohr provided compelling agreement with observation that couldn't be denied. Nobody knew why Bohr's model of the atom should work, and yet the best minds agreed that it did work. Why? Because in Bohr's physics, like Newton's, there's an agreement between theory and experiment that is quite simply too precise to ignore. Niels Bohr took the old physics and with his profound insight into the atom, propelled it directly into the future.
All right, so wins the 1922 Nobel Prize as a result. This guy's Danish. No, he's not a pastry, he's from Denmark. Notice that they got his picture on their currency. This sort of stuff is taken very seriously. Scientific and cultural achievements. It's a European thing. That sort of stuff is highly, highly, highly valued. All right, so moving forward. So what were the experimental proofs that Bohr's model of the hydrogen atom was correct? The size of the hydrogen atom. This was the ionization energy of the hydrogen atom. Experimental and theoretical numbers matched. That's it. As soon as the experimental and theoretical numbers match, that's the end of the game, guys. At that point, the final whistle, look at the scorecard. That's it, the game over. All right, so whether his theory made sense to other people or not, it did not matter. That's how science is. It's hard, cold facts. Look at the theory, the theoretical predictions in the numeric form, and look at the experimental facts in the numeric form. If they match, that's it. The theory becomes a scientific fact. So, he was able to solve the hydrogen atom problem. And then gets the Nobel Prize for it. Now, we're able to use this theory to explain stuff. Sky is blue. Why? Because blue light gets scattered more than any other color.
Electrons exist in an orbit or energy
All right, what do you see in the background? This is the black body radiation
level around the atom.
Ground state, and it wants to go to the first excited level.
Spectral line is produced.
Now, this is very interesting. And the
All right, guys, I don't know how well you're going to be able to see it unless the room is dark.
and will sit there in its ground state.
All right, so here's the electron orbiting the nucleus.
Suppose a photon comes along that has too much energy that actually would make it go between, say, not to the first excited state, but somewhere in between. That photon will also just pass through because it would leave the thing in a wrong spot. So it's only...
All right, so notice that the violence is coming in. Oh, it's going to have a frequency. The quantized frequency of it has to match the energy difference between the orbitals for it to become absorbed. This atom is going to look at it,
certain photon,
and then say, no, I'm not interested. It's going to go right through it because the frequency, when it's quantized, does not match the energy difference between the orbitals. So which means that this atom is going to be transparent to that color.
that can actually be absorbed.
It goes right through it as if there's no atom. Electrons are very picky. Electrons will only absorb the frequencies when quantized. It matches the energy difference between the orbitals.
Of course, once it's in the first excited state, it could then receive another photon to move it to the third or the fourth excited state.
Depending on the level of the transition, how far that electron jumps from a higher energy level down to a lower energy level, that electron may emit visible light, may emit ultraviolet light, infrared light, X-ray energy. It all depends. But whatever is emitted, the energy emitted is unique to the atom and hence the element.
This is the clue for discovering what atom is there, or one way of finding out, because each atom has a unique set of energy levels, so it has a unique set of photons that it can absorb, a unique set of wavelengths that it can absorb. So each transition between different levels gives out a photon of a very peculiar wavelength between. That photon will also just pass through. Suppose a photon comes along that has too much energy that actually would make it go between, say, a photon comes along that doesn't have enough energy to lift it.
When it makes the transition downward, emits this millionth to a billionth of a second. The electron
way is if a photon of just the right energy comes along, that electron can absorb that energy, kind of just take that photon out of existence, and it goes up to the next level, having basically eaten that energy. That energy kind of just
okay, guys, you can barely see it. Now the blue is coming in from
take that photon out of.
So what happens is the blue color is going to have the frequency when quantized is going to match the difference between two energy orbitals. So
resistance.
Okay, blue is coming in right from here. You can barely see it. The animation is cut off.
And it goes up to the next.
And then it gets absorbed, and now it jumps up. All right, and then what's going to happen is going to get released. This is going to stay here for a fraction of a second, and then it's going to get released.
Having basically eaten that energy.
That transition lasts for maybe a millionth to a billionth of a second. The electron then will make another transition back down from a higher energy level to a lower energy level. When that occurs, the electron must release.
All right, notice that now it's released. Notice that initially it was coming in this direction. Now it's released in a different direction. This is known as scattering. All right, so what's happening is the molecules making up the atmosphere, mostly nitrogen, absorb and remit blue light more than any other color, because the blue light has the frequency when quantized matches the difference between the energy orbitals of the hydrogen atom. Not the hydrogen atom, the nitrogen atom. As a result, blue light is scattered more than any other color. All right, so the absorption and re-emission of light is the reason why the light slows down these optically denser media. Absorption and re-emission of light by the atomic electrons is what slows it down. All right, electron absorbs the light. It's going to jump up to the next energy orbital. It's going to stay there for a fraction of a second. And upon jumping down, it's going to release the energy. All right, guys, this is where everything went to shit as far as Einstein is concerned. When the electron is energized and goes up to the next energy orbital, actually it hangs there, stays there for a fraction of a second. It's not like this. When you throw this up, it goes up and comes back down. It doesn't hang there. This motion is classical physics. This you can comprehend. When the electron makes a transition, it jumps up, it stays there for a fraction of a second, and how long it stays there is completely random. At that point, the randomness takes over. Cause and effect is taken out of the picture. And that really upset Einstein. Einstein introduced the probability theory into physics in 1916 to overcome this problem, because as far as he was concerned, that was a temporary solution to the problem. He thought that the probabilistic approach would stick around for a while until they figured out the problem, except that approach became the standard approach. So the quantum theory is a probabilistic theory. It's not a static deterministic theory. At that point, Einstein decided to turn away from the modern interpretation of quantum theory and decided to disprove the quantum theory, the modern interpretation of it, and spend the rest of his life working on it. All right, so other mystery can also be explained by using the Bohr's model. Red on top, blue is at the bottom. Red is on top because the color red is moving faster than blue through the material. So the question is why? All right, guys, take a look at red. Take a look at blue. Notice that the red is a smaller transition than blue. So this happens much quicker because it takes less time to make a transition from the third to the second energy state than from the fourth to the second energy state. Now listen, everything is explained. Orbitals. And there were a lot of questions that they didn't know how to explain. And on top of that, they couldn't generalize it to anything useful. All right, so what does the modern atom look like?
Science fiction writers have long predicted the ultimate advance. A mode of travel so fantastic, our every instinct tells us it can't possibly happen. The ability to transport ourselves instantaneously to anywhere on the face of the Earth or beyond. Teleportation.
All right, guys, just about every single technology that we're using today, inspired by Star Trek, the original from 1960s. The only thing we don't have today is the teleportation technology. Everything else came to pass, and the electronics that we have today is much more sophisticated than what they envisioned in the 1960s. Teleportation. Do you think we will ever be able to teleport one place to the next place, Star Trek style? I lied when I said teleportation. We don't have that technology. Actually, we do. The style of teleportation that we use today, using particles, is called entanglement. It's not the Star Trek style. I'm talking about Star Trek style. What is the Star Trek style? You take a person and you take this person and break this person into its atoms and molecules and turn it into a particle beam. And then send this particle beam to a given location and reconstruct the person back up from atoms and molecules into the person that the person was. All right, do you think we will ever be able to do that? All right, guys, I got news for you. This is the sort of stuff that happens to you, believe it or not, except it takes about 7 years. You're not the same person as you were 7 years ago. You don't have the same atoms and molecules. Everything gets recycled in your body. All right, the atoms and molecules making up your cellular structures are not the same atoms and molecules, except you quicken that process. All right, I will strip you into your atoms and molecules. I will break you down into your atoms and molecules. Instead of taking 7 years in terms of rebuilding you, I'm doing it within a fraction of a second. So what is the argument against that? Do you think we will ever be able to have this sort of technology? We'll find out. Take a look at this picture. Is this a he or she? And why do you care? Well, look at the details. Oh my God, look at the details. You can get this kind of this sort of details using a microscope. It's not the regular optical microscopes. It's an electron microscope. By using electrons, actually, you can come up with this kind of details, but which means that the electrons must be behaving like waves. Particles, could they ever behave like waves? We never will get to investigate. All right, this link is not going to work, but let's move forward. Grease, the movie Grease. What does the movie have anything to do with the quantum theory? Any ideas? You'll find out. I became a member of Facebook. I decided to join Facebook probably about 10 years ago. I don't like social media as much as most of you guys do. I was reluctant. The reason why I did it, because there was a way of communicating with students. I could put my stuff online, videos, the research or whatnot, and then and the sort of stuff that we tried to do using Canvas, the Facebook was really good at doing that sort of stuff. It still is in reality. And so when you're setting it up, they used to ask you these personal questions, the optional questions, and you would just answer them. You know, what's your favorite movie? I put down Grease. My wife wasn't too happy with that one. She said, Grease is your favorite movie? I said, yeah, it's an awesome musical. She said, yeah, but that's so gay. I said, no, honey, you could be straight and still have good taste. And so she was really, really pissed off about it for a long time. But the movie Grease is something to do with the quantum theory. So the question is what? We'll find out. Andrew Cleland's.
Experimental physicist Andrew Cleland had a chance of either receiving the energy or missing it. Instead, to his amazement, the pattern both receives the energy and misses it at the same time.
All right, so as soon as you see something like that, you go, oh, this is the Mandelbrot's interpretation.
And begins to oscillate between these two realities.
Which means that there are two possibilities, and both possibilities are taking place at the same time. And notice that that's one interpretation. That's not the only interpretation. The second interpretation.
And because it's not predicted, it's not something we can test. So that's generated to try to explain this. One of them is the many worlds interpretation.
All right, so where do we get the many worlds interpretation from?
Parallel universes. But in the end, those are not predicted. And because it's not predicted, it's not.
The other one is the Copenhagen interpretation.
There's a number of different interpretations that have been generated to try to explain this. One of them is the many worlds interpretation or parallel universes. But in the end,